Imagine you're at the top of a roller coaster and the car is still. As you accelerate down the hill, you go faster and faster. This is an example of conservation of energy. That is, potential energy at the top gets converted to kinetic energy at the bottom. Now clearly, energy in this case is a real number, but what if energy was perhaps something more complex? To answer that question, let's take a trip back to math class. Take a simple math problem like the square root of 4. The answer is 2, right? Well, sorta. There are actually two answers, positive 2 and negative 2. But what about the square root of a negative number like the square root of negative 1? You might recall that's an imaginary number, and we denote it with the letter I. A combination of a normal or real number with an imaginary number is a complex number. And the square root of a complex number is another complex number, but again there are two possibilities. And to understand this, we need something called a Riemann surface. To see what a Riemann surface is, we start by drawing the complex plane on a sheet of paper. Here x represents the real part, and y represents the imaginary part. The number 4 is here, and the complex number 4 minus 2i is over here. Now we'll take a second sheet of paper and we'll apply a little bit of glue along the minus x-axis to glue the two sheets of paper together right there. With a little folding, the shape of the paper represents the Riemann surface for the square root function. So the square root of 4 is right here on the surface. And if we think about slightly different values of that function, as we move around this paper, we can get different square roots. Something surprising happens when we hit that glue. We end up on the lower sheet of paper, continuing over to where the square root of 4 is equal to negative 2. This explains why there are two possible answers. Now if we make a smaller loop, we don't go through the glue, and we stay where the square root of 4 is equal to 2. So this shows us that there's something special about 0. That is, the square root of 0 is equal to 0. There's only one possible answer. So we've had this nice math lesson, but is there a way to see a Riemann surface in physics? It turns out there is, and that's where complex energies come into play. In our lab, we use a superconducting circuit to create an artificial atom with three distinct energy levels: the ground state G, the first excited state E, and the second excited state F. Now the state E is not stable, and it decays quickly to the state G. Here's the surprising thing. If we set the circuit in the upper two levels and just look at what happens when it does not decay, the mere possibility of decay allows the energies to be complex. A system has two parameters that we can tune, like the real and imaginary parts of a complex number. And since the energy is complex, the energy is now described by that Riemann surface we discussed earlier. And just like the Riemann surface for the square root function, there is the glue that holds the two sheets together and a special point, an exceptional point, where the two sheets touch. And the shape of this Riemann surface leads to something really cool. Now remember, we have two states, E and F, so that means in general there are two states of our system. Let's call them 1 and 2. Now normally, if we didn't have complex energies, if we started the system in state 1 and changed the parameters slowly, it would always stay in state 1. And that's what it means to be adiabatic. But with these complex energies on the Riemann surface, we can slowly change those parameters such that we go from one sheet to the other sheet. And this means that state 1 turns into state 2. And that happens just because of the shape of that Riemann surface that describes those complex energies. In future experiments, we plan to keep exploring this Riemann surface and create new quantum systems that have even more complex geometries and complex energies.